Hello, what's up to you all grade 10s? Welcome to the new slot. Guys, it's a promotion. I know that you guys are thinking already you're grade 11s, but we believe in you guys. We know that you guys are going to ace your exams and go to the next level, grade 11. My name is Abram and we're doing the show with Tracy today. Tracy, how are you?
I'm well, thanks, Abram. Thanks, Mindsetters, and I'm so glad you're joining us today because today we're going to be talking about paper 2. And like Abram says, we want you to ace those exams. So make sure that you are revising and studying hard so that you can really do your very best in those exams.
Of course, you don't have a reason to blame anybody else. We're here to help you guys use this opportunity. It's now or never. We've got notes for you guys. Go to land.mindset.co.za to get all our notes, including the schedule to check when is the next show, what is happening on our website, the competitions that we have. Go to that website. It's very simple, land.mindset.co.za. But for today's show, we've got the notes, download and view option available for you guys from facebook.com/LandExtra. Also send us some tweets, questions, comments on @LandExtra. I'm here to take your questions as well, guys. So we're ready for this show. Let's do this, Tracy.
Thanks so much, Abram. So, Mindset, as we said, we're going to be tackling some exam questions, and specifically, we're going to be talking about paper 2, which is your chemistry. So, we spoke last week about physics, but today we're going to be speaking about chemistry, and we want to revise some concepts of atoms, chemical formulae, which I know is challenging for many of you, and writing equations. We want to solve chemical calculations using mole ratios and the whole mole concept, so we'll revise that. And we always are wanting to practice answering exam type questions. So there's lots to cover today because your paper 2, your chemistry section, has certainly got lots of interesting challenges. So I really hope that you're going to join with us today and get your thinking caps on. In light of that, I want to give you a challenge question. And the challenge question is asking you to calculate the number of protons in a sample of 1.74 kilograms of lead. Now, this is interesting. There's certainly lots on the go here. And I want you to make sure that you go and take, it looks like quite a simple question, but I need you to go and think through number of protons in that mass of lead. So you're going to need to go and get your calculator out and get working on that. Let's go through some questions for today. So question number 1, we are asked about uranium. Uranium is a reactive element. 2 of its isotopes are uranium-238 and uranium-235. Now, interesting, I'm underlining the word isotopes and then those 2 isotopes that they give us. We're going to probably be asked about them. A sample of uranium is found to have 99.3% of uranium-238 and 0.7% uranium-235. Firstly, they're asking us to define some terms. And the first term is what is an element, because they spoke about here, uranium is an element, a reactive element. So what is an element? This goes back to our fundamentals when we talked about mixtures and pure substances. An element is a pure substance that cannot be broken down by any chemical means. It is a pure substance that is made of only one type of atom. So if it's helium, then whatever you do to it, whether physical or chemical, you can't separate those atoms into anything other than helium atoms. Okay? It is one type of substance that cannot be broken down by chemical means. As opposed to a compound, which is a pure substance, but it can be broken down by chemical means. Because if you had something like water, is a pure substance made up of 2 types of atoms, and those 2 atoms would be hydrogen and oxygen. That would be a compound. Whereas an element, only one type of atom, so it can only be broken down through chemical means. Next question: what is an isotope? So an isotope of an element is when you have two different varieties, if you like, of the same element. So an isotope, and I'm going to actually write here isotopes have, that would be even better. Isotopes have the same number of protons, and remember the proton number is the number of protons, or the atomic number is the number of protons inside an atom, and that is unique to each element. So it's got the same number of protons, it is the same type of element, but a different number of neutrons. Okay, different number of neutrons, which means its mass is going to be heavier or lighter, but it's still got the same number of protons, so it's still the same element. And if you'll notice, at the top here, they give uranium-238 and uranium-235. Now, it might be helpful for us to flip across to a periodic table and find uranium on the periodic table. Okay, it is the U on the periodic table. We'll find it in a minute. Uranium-238, is it even on this periodic table? I don't see it here. I'm looking for it, but I don't see it. Because as you know, our periodic table does continue. This is just a shortened version. Uranium-238, we'll need to write it in standard notation. And what I want you to notice for standard notation, what you're looking at there is the element, and I'm just going to sketch it here, the element with the X, I'm just doing a random one, with a number at the top, okay, and this number at the top, and then a number at the bottom. The number at the top is going to be the mass number. The number at the bottom is the atomic number. And if you notice on the periodic table, this is what is given to you, but not in standard notation. And each periodic table will be different, so it depends on which one you've got. Notice here, they're giving us the mass at the bottom and the atomic number at the top, but that is not standard notation. And so when you write this, you have to write it in standard notation. So, uranium, and I've got two isotopes. So the one is going to be 238, and the other one is going to be 235. Notice that is the mass number. And I didn't see it on my periodic table, but it is element number 92. Let's spot it again. 80. Ours doesn't get as far as there it is, sorry. Down at the bottom. Element number 92. And so we would write there 92 as the number of protons. That is the standard notation. And remember, standard notation, you've got the mass number at the top and the atomic number at the bottom. Then they ask us to calculate the relative atomic mass for this sample of uranium. So how are we going to do that? Well, we're going to certainly need our calculator, but what you're going to do is say, imagine you have got, in that sample, you have got 99.3% of the uranium-238. Okay, and you had 0.7% of the uranium, what is it, 235. So how are we going to work that? Well, we're going to need to say, well, what contributes, what does this 99.3 contribute to the mass? So what you're going to do is say 238, which is the mass, multiplied by 99.3 divided by 100, or 99.3%, and you're going to work that out. Okay? You're going to do exactly the same for the other one. So 235 multiplied by 0.7 divided by 100, or 0.7%, and we would work that out. Then we'll take our two answers and add them together. So let's start with the first one. Just going to put our calculator on the side here. So it's 238 multiplied by 99.3, and I'm going to say divided by 100. And we get our answer 236.33. 236.33. That's not my final answer, but I'll come to it in a moment. Then I'm going to do the same for the isotope of uranium-235 multiplied by 0.7 divided by 100 equals 1.64. Actually 1.65 rounded off. 1.65. Now I need to take these two answers and add them together. So 236.33 plus 1.65 and 236.33 plus 1.65, and I get my answer 237.98. 237.98 atomic mass units, AMU. And that is the relative atomic mass. And the reason it's relative is because it's taking into account those different isotopes to make up that value. And what you'll see sometimes on the periodic table, and I'm going to look for a couple of them. Notice copper is 63.5. Another one that's common is chlorine, 35.5. The reason for that is because there are different isotopes, and because of those different isotopes having different masses, they would need to take those into account. So we've done it for uranium, and most samples of uranium have quite a high percentage of 238, which is why it's so much closer to that value. Okay, next question. Calcium chloride can be decomposed through the process of electrolysis by passing an electric current through an aqueous solution of calcium chloride. So a couple of things to pick up. We've got a sample. It can decompose. What does decompose mean? It means to break down. So that is going to be helpful. It means to break down through the process of electrolysis. And you should know what electrolysis is. Electrolysis, it means to split or to separate. And electro, so lysis means to split. Electro would be through an electric current. So an electric current is passed through the sample and it is separated. Through an aqueous solution, I'll come to that in a moment, of calcium chloride. Solid calcium and gaseous chlorine are formed. That's the introduction, and it's always valuable to read through those introduction points, because if once you've read through them, there's going to be lots of information that you can gather from that. So I think it's important now that we take a short break, and when we've come back from this break, we'll answer this question and the sub-questions from it. Thank you.
Thank you so much, Tracy. Remember, my sisters, every accomplishment in life, it always starts with a decision and willingness to try. So we do have a challenge question that would like you guys to try. Give it a try. Don't just say it's difficult. We'll see you after this break. Welcome back, awesome grade 10s. I'm waiting for you guys to send me your questions on Twitter at LearnExtra, and also on our Facebook page, which is facebook.com/LearnExtra. Even Tracy is waiting, guys, to help you guys. We're eagerly waiting. So send those questions through, relevant questions for grade 10s.
Thank you so much, Abram. Very important that you do challenge yourself, because that is how you learn and how you develop in your thinking and understanding. So mindset is, I started with this question just before the break and just introduce the question. So we've got calcium chloride, it's decomposing through electrolysis, separating into its components, and they tell us that it's an aqueous solution, but at the end of it, solid calcium and gaseous chlorine are formed. So, state what is meant by the term aqueous. Now, that word aqueous is an important definition, and what it means is dissolved in water. And the subscript is AQ. And very interesting things happen when things are dissolved in water. And if you think about life on Earth, it wouldn't really be happening. Things moving around your body even taking place in water. So a lot of chemical reactions occur in water, and it's incredibly important that you understand what we mean and when we talk about aqueous solutions. Write down the formulae of the ions present in this solution. So if you can imagine, what we've got is a beaker with 2 electrodes. Okay? And in those electrodes, it's connected to something else. Within that, there is a solution. And that solution has got calcium chloride. Now, what I really want you to do here is consider what are the ions that make up calcium chloride. So firstly, you've got to go across to your periodic table and find where calcium is. Here it is. And where chlorine is. And let's talk about calcium first. Notice that calcium is in group 2, which means that when it forms an ion, it's going to lose 2 electrons, and so that it can have a filled outer energy level. So it's losing 2 electrons, almost like 2 little jumps back, so that it has the same electron structure as argon, right? Why do I say that? Well, because it has 20 protons, so 20 electrons. If it loses 2 electrons, it's going to have 18 electrons, and so a filled outer energy level. If we head back here, so calcium, we said, was going to lose 2 electrons, which means it forms a 2+ ion. Why? Well, because if it has 20 protons and only 18 electrons, the positives outweigh the negatives, and so here it's forming a 2+ ion. And anything that is in group 2 would form a 2+ ion when as it loses 2 electrons. What about the chlorine? Well, the chlorine, when it forms a chloride, notice the name changes, it is forming a negative ion because it wants to gain electrons, and so it's moving that way. It takes up an extra electron, so instead of having 17 electrons, it's now got 18 electrons, which means it's going to have filled outer energy levels. So, going back here, the chloride becomes chlorine, and it's got a 1- charge. Thinking about that, you would notice there actually would be 2 of them, in the ratio of 1:2, but the negative charge there is only 1- because each chlorine has taken up 1 extra electron, forming a 1- chloride ion. Could a current pass through a sample of solid calcium chloride? So if we had just a lump of calcium chloride, would an electric current, if I put the little electrodes or crocodile clips across it, would the current pass through that? Question, would it or wouldn't it? Well, you need to consider here, what do we mean by a solid? A solid is going to have those those ions would be held in the crystal lattice. And so yes, they are charged because ions are charged, but those charged particles, are they free to move? And the answer is no. So could a current pass through a sample of the solid? No. Why not? the ions are held in the crystal lattice, and so I'm just erasing that and writing here, charges are not free to move. Because although they are charged particles, they are held in that crystal lattice, locked in position, and so are not allowed to move around, and so therefore cannot conduct that electric current. So, this electrolyte solution has got the calcium 2 plus and the chloride 1 minus ions, and they are free to move because they're in solution, because they've been dissolved in water. So, suggest 2 factors which could increase the conductivity of this electrolyte. Make sure you know the definition of what we mean by an electrolyte. An electrolyte is a solution with charged particles that are free to move. How could we increase the conductivity, the ability to conduct an electric current? Well, now you need to think back to a little bit more in terms of your kinetic molecular theory. If we increase the temperature and had this thing happening at a higher temperature, you would know they would have a higher kinetic energy. So therefore, the particles would move faster, which means they are conducting that current and allowing it to go a lot faster. The second factor, because they asked for 2, so that was our first one, higher temperature. The second factor we need to look at is how many of these charged particles there are per unit volume. And that would be a concentration. Of ions. If we increase the concentration of ions, there are going to be more charged particles to conduct that current. And so certainly those are 2 factors which could increase the conductivity of this electrolyte, of this current carrying solution. Next, we're asked to write an equation for the decomposition of calcium chloride. Now, I know many of you struggle to write equations. So let's take this quite slowly, and then they ask us to include state symbols, so solid, liquid, gas, etc. Firstly, I wanted to start with writing out what we understand by calcium chloride. Now remember, I had Ca2 plus and Cl minus. When those things come together, they are forming calcium chloride with 2 chlorines for every 1 calcium. That's important to note because go back to the ions. Notice that when we put those ions together, they need to be in a ratio that would result in 0 charge. So you've got a calcium 2 plus and a chloride 1 minus. That means you need 2 chloride ions for every 1 calcium ion. And so when we write it, it's calcium chloride, and that forms calcium that is solid. I'll write those in a minute. Calcium and chlorine. Now hold on a minute. I want you to identify the calcium is fine, but the chlorine is diatomic. And that 2 there has nothing to do with this 2 here. This 2 is because chlorine is a diatomic gas, and so what's going to happen is that the chlorines are so reactive that they're going to bond with each other covalently and form a diatomic gas. So now we need to go back and fill in our state symbols. This we know was aqueous. Why? Well, because they told us at the beginning. This thing is solid, also they told us, and that is a gas. Remember that it is incredibly important for you to go back and read the information that they give you. Solid calcium and gaseous chlorine are formed. So you don't have to sit there wondering what is it that I'm supposed to write. They instructing you and they're telling you. So read the information very clearly, because that will guide you. Then we need to check, is it balanced? Yes, in this case it is. Name the law that a balanced equation represents. Well, when we talk about a balanced equation, we're always thinking about the conservation of matter. That matter cannot be created or destroyed, it is maintained. Then one last thing, and I've just added this on as a sub-question. Tell me, is this an example of a physical change, or is it an example of a chemical change? Think about it. Is it a physical or a chemical change? What do we mean by physical change? Physical change means the substance doesn't change, it just simply changes state. It changes its form, but it's still the same substance. Chemical change? The chemicals undergo some kind of change and form new substances. Well, definitely it must be a chemical change. So it is a chemical change, not a physical change. And this is an example of a chemical change. I think we've got time to introduce one more question before our break. Ammonium carbonate, you notice I've given you lots of chemical ones to work out. Decomposes, again, breaks down according to the following equation. Ammonium carbonate forms ammonia and water and carbon dioxide. Write formula for and balance the word equation. Now, I know you're sitting at home and thinking, how do you even start? Well, firstly, it's important that you write down what you know. So if you come across something, write down what you know. Certainly you know the formula for water, and you know the formula for carbon dioxide. That's a given. But then there are a few others that you should know. Ammonia, definitely, is NH3. And ammonium is NH4 plus. Now, what you'll notice, I'm writing it above here because this is my working out step. Okay? The next one I want to notice is this carbonate. Carbonate is another polyatomic ion, like the ammonium, that I would want you to know. It will help you. Carbonate is CO3, 2 minus. And so I can come to the next line and I can write down this whole formula. And notice I've once again got an issue here with the 1 plus and 2 minus. The previous one with calcium chloride, I had the calcium was 2 plus and the chlorine was 1 minus. And so you had to balance those charges. In the same way here, we're going to have to balance the charges. But it's slightly more difficult because I don't want just one extra hydrogen. I want 2 of this whole ammonium ion. So how do we do that? Well, we're going to have to write it in brackets. So I'm writing NH4, but notice I want 2 of them. And then I can continue CO3. Notice I'm not now writing the charges at the top because I've balanced the charges, so there's no need to write them out again. And that forms NH3 plus water plus CO2. Now let's have a look and see if this thing is balanced. So, and you don't have to write those in different colors. I'm just highlighting it for you so that we can very clearly see it. And let's go to green here. Notice I've got 2 nitrogens on this side, but only 1 nitrogen there. Now that I've written the individual formulae, I cannot go and change those small numbers. I can write big numbers in the front, so there's going to be a 2 in the front of that. And that's going to make 2 nitrogens and 4 times 2, which is 8 hydrogens. So how many? That's 2 times 3 is 6, plus another 2 is 8. Carbons 1, 1, oxygen 3, 2 plus 1 is 3. And so it's balanced. Now when we come back from the short break, we'll continue with this question and make sure that we answer all these, and I know they're chemical calculations, so it's important to stay tuned. Thanks, Abram.
Thank you so much, Tracy. And guys, thank you for your answers for the challenge question. Keep them coming because after this break, we'll also be answering your challenge question. Stay tuned. Welcome back, Mindsetters. Now, we love listening to you guys, but we also want you guys to download the notes. Get the notes, download them or view them. The links are up there on our Facebook page, facebook.com/learnextra, or go to our website, learn.mindset.co.za. For now, Tracy, I've got a question for you.
Excellent. Thanks, Abram.
Lungi says, how does one determine which compound or compounds are aqueous or not in a chemical equation?
Okay, so this goes back to your solubility rules, and it's helpful for you to go and work through those. Couple of key points. Most ionic substances are soluble because if you think about, they have ions, and so those ions will be attracted to the positive ions will be attracted to the negative part of the water, and the negative part would be attracted to the negative pole of that dipole of water. So most ionic substances are soluble, but there are some that are not. And here I want to advise you to go back to your solubility rules. Things like lead-based salts, mercury-based salts, those can be insoluble, and silver-based salts can be insoluble. Your carbonates are often insoluble. So you would need to go back and revise your solubility rules in that chapter on aqueous solutions, and that will really help you. So go back, but majority of them would be ionic substances, would be soluble in water. Excellent.
Awesome.
Thanks so much for that question, and it's so important that you do interact with us. Going across to this chemical calculation, they ask us to determine the molar mass of ammonium carbonate. Now, I always write down the substance that I'm working with. So I write molar mass, and I write in the formula of what I'm working with. It's NH4 in brackets 2 CO3. Then I can go to a periodic table and I can look up all of these different things. Now I know we don't have that much time, so I'm just going to circle. Nitrogen is 14, hydrogen is 1, carbon 12, and oxygen 16. So I'm circling those, and I've shown you where we'd find them. Now we need to write this out. So firstly, I'm going with equals 2 times whatever's in brackets. So what was there? There was 1 nitrogen and 4 hydrogens. Then I had carbon, which was 12, plus 3 times oxygen, which was 16. And I'm going to go across to my calculator, and I'm going to work this out. 16 times 3. I'm going to do them in different parts. So that one was 48. 48 plus the 12, and 14 plus 4, because 4 times 1 is 4, so 14 plus 4 is going to give me 18. 14 plus the 4, 18, and I'm multiplying that by 2 to give me this whole term was 36. So 36 plus 12 plus 48, 36 plus 12 plus 48 is equal to 96. And my answer here, 96 grams per mole. Calculate the number of moles if 336 grams of ammonium carbonate react. So, the number of moles, how are we going to do this? Well, we have an equation. Number of moles is mass divided by molar mass. So, I have here 336 grams in my sample divided by 96 grams in every mole, grams per mole. And that's going to give me, well, 336 divided by 96, 3.5 moles. 3.5 moles react. Then, what volume of ammonia gas is released through this reaction at STP, which means standard temperature and pressure? Now, this is a very interesting question because it's got to do with our balanced equation. Now, I want you to notice here, there's an understood one there. It's not written in, but it's understood. You don't write 1x, you can just write x in maths, yes? In the same way, we don't have to write a 1 in here, but there is a 1. And what we need to look at in the balanced equation is this mole ratio. So that is a 1:2 ratio. And so getting from what I have, which was 3.5 moles of ammonium carbonate, to the number of moles of ammonia, it is a 1:2 ratio, which means that if I had 3.5 here, double that would be 7, because 3.5 times 2 is going to give me 7. So therefore, 7 moles of ammonia are formed. That's the first step. But they're asking me specifically about the volume of ammonia. So how do I do that? Well, number of moles is the volume divided by the molar volume at standard temperature and pressure. So volume is going to give me number of moles multiplied by the molar volume, and that is, well, 7 moles multiplied by the volume of 1 mole at standard temperature and pressure, which is 22.4 decimeters cubed. And every 1 mole of any gas will take up, at standard temperature and pressure, will take up 22.4 cubic decimeters of space. So that's quite a useful one. It is on your data sheet. Multiplied by 22.4 equals 156.8. 156.8 decimeters cubed. And that is our final answer, because it was asking what volume, and we've given them the volume of how many of ammonia that would be formed. The last question is our challenge question. And this might seem like a relatively short question, but there's lots in it. So let's start at the top. Calculate the number of protons in a sample of 1.74 kilograms of lead. Okay, so where to begin? Well, firstly, I've got to start with the information that they give me, which was the mass of lead. So I want to recommend that we go to our periodic table and we go and find lead. And lead is Pb, which is over there. And a number 82 is useful, and a number 207 is useful. So let's write this. Lead Pb, remember standard notation, 207 and 82. That's helpful. So I need to write number of moles is mass over molar mass. The mass they give me as 1.74 kilograms. Now kilograms I need to convert to grams. Why? Because my molar mass is going to be in grams per mole. So the first thing I need to do is always to go and work out. We don't even need to work it out. Can we just substitute 1.74 times by 1,000? And that needs to be divided by 207. Why? Because the molar mass of the lead is going to be its atomic mass in grams per mole. So 207 grams per mole. And the kilo stands for 1,000. So I think I've got enough there. Let's go to our calculator. 1.74 times by 1,000 is going to give me 1,740 divided by 207 divided by 207 and that's giving me 8.405. So I'm going to need to round up. 8.41 moles of lead is what I've got in my sample. Has that answered the question? No, that has told me how many moles I've got, but that has not told me how many protons I have. So we need to go one step further. And for that, I need to then say, my next question is how many atoms are there? Well, how many atoms in 8.41 moles? The next one we need to think about is Avogadro's number, and this is number of particles divided by 6.02 times 10 to the 23, which is written as number of particles, in this case it's going to be atoms, divided by Avogadro's number. And Avogadro's number is the number of particles, or the number, in this case, the number of atoms in every mole. And it's a huge number, 6.02 times 10 to the 23 particles. So, what do? Well, I'm going to have to rearrange this equation because I've got the number of moles, but I'm looking for the number of atoms. Is going to give me the number of moles I've got multiplied by Avogadro's number. So I can substitute. This is what I had, 8.41 moles of lead. And I need to multiply that by how many particles, or atoms in this question, in every mole. So back to our calculator. 8.41 multiplied by 6.02 times 10 to the power of 23. And it's giving me a huge number. Of course it's giving you a huge number because it's asking you how many atoms are there in that lump of lead. There are, I don't even want to say millions because it's far more than that. It's 10 to the power of 24. So 5.06 times 10 to the power of 24 atoms of lead. Now have we answered the question? Not yet. Why? Because I'm giving how many atoms there are. But what did the question ask? The question asked me how many protons there are. So, once again, how many protons are there? And I want to come back to how I've written the standard notation. Notice that there are 82, that's the atomic number, which is the number of protons. So if you think about it, for every atom of lead, there are 82 protons inside its nucleus. I'll say that again. For every single atom of lead, there will be 82 protons inside that nucleus. So, I first in this question worked out how many moles of lead I had. Then I worked out how many atoms of lead would there be in that number of moles. Now, in this last part, I need to work out how many protons there are. So, for every atom of lead, there are 82 protons. Which means I need to take my answer from the previous step, which was 5.06 times 10 to the power of 24 atoms. And I need to multiply that by 82. Where did I get that 82 from? From the periodic table. And I'm just going to clear this here. And once again circle the whole thing. There we had at the top, that is the atomic number, which is the number of protons. So that's how I'm getting that piece of information. So we come back to our calculator and we say 5.06 multiplied by 10 to the power of 24, and each atom has 82 protons. So my answer here was 4.14, I think it was 4.14, but I'm needing to round up. So notice there, the next number is a 9, so we round up. 4.15 times 10 to the power of 26 protons inside the nucleus. Well, 82 inside the nucleus of each atom, but in that whole 1.74 kilograms of lead, there are going to be that number of protons. 4.15 times 10 to the power of 26 protons. And it's very helpful to think through what we've done in this whole process. We were given a mass, and from that mass we converted to number of moles. From number of moles we worked out how many atoms there were, and from how many atoms there were we worked out how many protons there would be. So that's quite a detailed question, but I knew it would be because it was your challenge question, and of course we're always wanting to challenge you. So mindsetters, I hope that has helped you to think through the process of how you would answer something like this. Remember to keep your thinking caps on to make sure that as you're studying and as you work, you are really answering what the question is asking. And I do encourage you to work with SI units, to convert to SI units, and make sure you're answering those questions. Abram, are there any questions on the page?
Yes, there are some questions, and I'd love you to give the mindsetters some tips, for their paper. Here's a question from Bomi on the previous question before the challenge question. Why current is not moving in solid?
Okay, I'll go back to it. I think it was the previous one, question 2.
Yes.
Here we had charged particles, but those charged particles, if it's a solid, are held in place, locked in the crystal lattice. If you think about something like sodium chloride, you have one sodium, one chloride, one sodium, one chloride, and there are strong forces of attraction between them that are locking them in place and not allowing them to move around. So when they're in a solid, that crystal lattice structure is holding those charged particles in place, and so they can't move, which means there can be no flow of current.
All right. Another one from Ben. What is the electronegativity difference between BE and C?
Okay, between BE and C. So let's turn to our periodic table. Between BE and C, which is carbon. So here you would turn to your periodic table. These are not numbers I necessarily keep in my head all the time. And I want you to notice I've circled the ones in yellow. So the electronegativity is given to you on this periodic table. It's written on the side there. So carbon has an electronegativity of 2.5. Beryllium has an electronegativity, I think that's 1.5 it is, of 1.5. So 2.5 minus 1.5 electronegativity difference of 1. Hope that answers your question.
Awesome. Thank you so much. Your tips to help the mindsetters?
Mindsetters, study your definitions. Make sure you know your definitions. Once you've done that and you know your theory, make sure you answer as many questions as possible. And as you do that, make sure that you can apply your knowledge as best as possible. I really wish you everything of the best for your chemistry exam and your physics exam as you study and work through this, this grade 10 year. From me, Tracy, this is my last show with you. I'm moving back to Port Elizabeth with my family, and so I need to wish you well and say I've really enjoyed this time together with you.
Thank you so much,
I really
Tracy.
hope that this has inspired you to continue with science and and really encourage your friends as well to continue with science. It's been an absolute joy and a privilege and a dream come true for me to present to you, and I really wish you everything of the best. I know that God has got a plan and a purpose for your life, and that it's been a joy for me to be part of it. So thank you so much.
Thank you so much, Tracy. It's been a great pleasure working with you. We really appreciate you and all the best in all that you do. Mindsetters, thank you for tuning in, and a big thank you to our sponsor, MTN SA Foundation, and also the Department of Basic Education for endorsing this program. We love you, and peace.